Mars has captivated scientists and the public alike for centuries. One of the biggest reasons is the planet's reddish hue, earning the fourth rock from the Sun one its most popular nicknames, the Red Planet. But what exactly gives the planet its iconic color? Scientists have wondered this for as long as they've studied the planet. Today, they may finally have a concrete answer, one that ties into Mars' watery past. Results from a new study published in the journal Nature Communications and led by researchers from Brown University and the University of Bern suggest that the water-rich iron mineral ferrihydrite may be the main culprit behind Mars' reddish dust. Their theory, which they reached by analyzing data from Martian orbiters, rovers, and laboratory simulations, runs counter to the prevailing theory that a dry, rust-like mineral called hematite is the reason for the planet's color. The fundamental question of why Mars is red has been thought of for hundreds, if not for thousands of years, said Dumas Valentines, a postdoctoral fellow at Brown who started this work as a PhD student at the University of Bern. From our analysis, we believe ferrihydrite is everywhere in the dust and also probably in the rock formations as well. We're not the first to consider ferrihydrite as the reason for why Mars is red, but it has never been proven the way we proved it, now using observational data and novel laboratory methods to essentially make a Martian dust in the lab. Ferrihydrite is an iron oxide mineral that forms in water-rich environments. On Earth, it is commonly associated with processes like the weathering of volcanic rocks and ash. Until now, its role in Mars' surface composition was not well understood, but this new research suggests that it could be an important part of the dust that blankets the planet's surface. The finding offers a tantalizing clue to Mars' wetter and potentially more habitable past because, unlike hematite, which typically forms under warmer, drier conditions, ferrihydrite forms in the presence of cool water. This suggests that Mars may have had an environment capable of sustaining liquid water, an essential ingredient for life, and that it transitioned from a wet to a dry environment billions of years ago. What we want to understand is the ancient Martian climate, the chemical processes on Mars, not only ancient but also present, said Valentines, who is working in the lab of Brown planetary scientist Jack Mustard, a senior author on the study. Then there's the habitability question. Was there ever life? To understand that, you need to understand the conditions that were present during the time of this mineral formation. What we know from this study is the evidence points to ferrihydrite forming, and for that to happen there must have been conditions where oxygen from air or other sources and water could react with iron. Those conditions were very different from today's dry, cold environment. As Martian winds spread this dust everywhere, it created the planet's iconic red appearance. The researchers analyzed data from multiple Mars missions, combining orbital observations from NASA's Mars Reconnaissance Orbiter and the European Space Agency's Mars Express and Trace Gas Orbiter with ground-level measurements from rovers like Curiosity, Pathfinder, and Opportunity. Instruments on the orbiters and rovers provided detailed spectral data of the planet's dusty surface. These findings were then compared to laboratory experiments, where the team tested how light interacts with ferrihydrite particles and other minerals under simulated Martian conditions. Martian dust is very small in size, so to conduct realistic and accurate measurements, we simulated the particle sizes of our mixtures to fit the ones on Mars, Valentines said. We used an advanced grinder machine which reduced the size of our ferrihydrite and the salt to submicron sizes. The final size was 1/100th of a human hair, and the reflected light spectra of these mixtures provide a good match to the observations from orbit and red surface on Mars. As exciting as these new findings are, the researchers are well aware none of it can be confirmed until samples from Mars are brought back to Earth, leaving the mystery of the red planet's past just out of reach. The study is a door-opening opportunity, Mustard said. It gives us a better chance to apply principles of mineral formation and conditions to tap back in time. What's even more important, though, is the return of the samples from Mars that are being collected right now by the Perseverance rover. When we get those back, we can actually check and see if this is right.